the island of La Palma, one of the lesser-known Canary Islands off the coast of Africa. It's not very big, and it has only one fairly busy town, Santa Cruz, and all towns in the Canaries seem to be called Santa Cruz. It's not a tourist centre, like some of the other islands, but it has become of tremendous importance scientifically. It has an extinct volcano, Los Muchachos, and on top of this is a major observatory. The newest telescope is the William Herschel Telescope, the culmination of years of work. And when we visited La Palma recently, it was about to have its first light. It's the third largest telescope in the world. The project engineer of the William Herschel Telescope is Brian Mack.
At the moment, we're actually shaking the telescope. We're actually carrying out servo-controlled tests to find out the natural frequencies, the hysteresis, the drive features, to find out how frequency response characteristics occur. We'll be doing this for the next week or so, and then we will actually be putting in the optics.
Speed. Here we go. Are you ready? Yeah. 3, 2, 1, go.
At the moment, we have actually dummy optics in the telescope, because of course we don't really shake the mirror or shake the secondary mirror. They're so expensive and they're very fragile.
Stopped.
After this, we will be doing the on-the-sky tests, which will be the optical alignment of the telescope before we actually put an instrument on the telescope to do observing.
This is an altazimuth telescope. That means you've got to drive it not only east-west, but also up and down. So it's two separate systems.
Basically, the drive systems have got to be very accurate, much more accurate than in an equatorial telescope, and much more responsive. When we get to the zenith blind spot, where we get the telescope where the tube is completely vertical, we then have to turn the whole 210 ton through very quickly. And this means accelerating 210 ton to move the telescope around another 180 degrees in order to pick the star up again for any star that goes through zenith. This means, of course, a very stiff telescope requirement, a very accurate servo system. The gears that encode it are very expensive gears. In fact, the gears themselves are the largest, most accurate gears ever produced in Europe in the last 10 years.
What about balance?
In fact, it's balanced to about 3 kilogram meters. So in fact, you can basically push it with your finger.
I know that everything has to be tremendously accurate. What is the admissible error? It's the tiniest fraction of a millimeter.
In fact, a fraction of a millimeter is not acceptable. We're actually talking about microns. We're talking about much more than, less than a fraction of a millimeter. An example is that the telescope's 210 ton. It's actually floating on oil. The oil bearings have 90 microns gaps. That is 4,000ths of an inch. That's the thickness of your hair.
How long have you been working on the telescope?
11 years.
And has it really come up to your expectations?
Not yet.
It will.
We'll finish it. When we get onto the sky, you can't really tell until you actually get onto the sky, and the sky's the proof. So far, engineering-wise, electronics, electrical, software, it's showing up very well. But you still can't prove it until we're actually on the sky.
The main task of a telescope is to collect light. The William Herschel Telescope is very good at this, partly because it has such a large mirror, and partly because it's operating under really splendid conditions above the worst part of the Earth's air. But remember, once you've collected your light, you've got to use it, and that's a different kind of problem. The old-fashioned photographic plate is being replaced by ultra-modern electronic devices, without which even a huge telescope would be limited. The William Herschel Telescope will use the very latest electronic equipment. One man who's played a really major role in developing it is the director of the Royal Greenwich Observatory, Professor Alec Boxenberg.
Well, the instrumentation is all important. Without the instrumentation, a telescope wouldn't be any use at all. If you try to look through the eyepiece, if there were one, the amount of information you'd get would be extremely limited. So the instrumentation is what makes the telescope. And quite recently, perhaps in the last 2 decades, the power of all telescopes has increased maybe by 10 or 100 times simply because of the instrumentation.
What special kinds of instruments are going to be used on the William Herschel Telescope?
Well, of course, we'll be looking at images. For that, we'll use photography in the usual way. but mostly CCDs, which are solid-state devices, and they go very much deeper, but with a much smaller field. But actually the most commonly used technique is spectroscopy, the technique where you spread the light out into colours and use that to analyse the nature of the object. But there will be new types of instrument as well. Each focus will have an instrument attached. In this telescope, there are 3 accessible foci, the Cassegrain, which is at the base of the telescope, and 2 Naismith foci. They can be addressed with a rotating mirror in just a few seconds, so that instruments mounted there can be brought into operation very rapidly. But there's also the prime focus. That takes a little bit more effort to get going on a given night, but still only about half an hour is required to get that operating. So there's 4 stations, and at each station there'd be a unique instrument. And one of the main new types of instrument we'll be looking at one of the Naismith foci is to investigate ways of stabilizing or effectively stabilizing the atmospheric tremor, a process we call image sharpening, and also using techniques such as speckle interferometry and aperture synthesis methods, as are used in the radio, to get very high resolution images, much higher than could ever be achieved before.
Why was La Palma chosen?
Well, La Palma was on the list of several possible good sites around the world, and each one was tested very carefully over a long period of time. In fact, La Palma was tested over a period of 18 months, for example. And quite simply, it was the best of the lot. For optical astronomy, La Palma is correctly sited, has on it a mountain of roughly the right altitude. It has very stable atmospheric conditions, very low cloud cover, and all that sort of thing, which makes it the perfect site for optical astronomy, and that's why we picked it.
So the telescope's complete, and I take it you're perfectly satisfied with the choice?
Perfectly satisfied. We've had a lot of experience with the other telescopes already, which show that the choice was correct, and I'm absolutely confident the William Herschel Telescope will perform in just the way we expect it to.
When you're building a big telescope, I suppose about 50% of the problems are engineering, and the other 50% are optical. And obviously, the main component optically is the big mirror of the telescope. And this rather strange-looking construction is the illuminizing chamber, inside which the mirror is kept until it's ready to be put into the telescope. It is being brought out now especially for us, and I think we are some of the first people to see it like this. Now, this mirror is 165 inches, or 4.2 meters in diameter, and it weighs 16.4 tons. And there are only 2 telescope mirrors larger than that. The Russian 236-inch, which frankly isn't very good, and the Panama 200-inch, which is now 40 years old. Now, you may think that the mirror looks fairly reflective, but that's not good enough to satisfy astronomers, which is why the mirror has to be coated with a very thin layer of aluminium, only a few microns thick, a micron being a millionth of a meter. And that's done inside this illuminizing chamber, which costs more than £500,000 and is in use on this mirror for only about 1 hour per year, but the telescope wouldn't really work effectively without it. Now, the mirror itself has got to be amazingly accurate. We are talking about accuracy to something like, 1/40th of a micron. And you can imagine how difficult that is. Note also the hole in the middle. That's because for some optical systems, it's necessary to bring the light to focus behind the main mirror. It's really what most people know as the Cassegrain optical arrangement. Originally, in the photographic era, the astronomer using a large telescope had to spend many hours sitting at the eye end of his telescope, continually adjusting to make quite sure that the object he was photographing was kept in view. But things are very different today. When you're observing, the observer certainly won't be in the actual dome. He may not be in the same building. He may not even be in the same country, because everything is completely computerized. And here, with the William Herschel Telescope, we have a large and comfortable control room, and Stan Atkinson's in charge of it.
In the case of an alt-azimuth telescope, you're basically driving 3 axes simultaneously. And we have to follow objects which are following a curving path in the sky. And consequently, we have a group of objects, perhaps on this path, as they move through the curvature, then you're rotating the telescope in altitude and azimuth, which basically tracks the group. But you have to compensate for rotation of the group by moving the field rotator. The altitude and azimuth drive is essentially we rotate the telescope in azimuth, which is rotating it in a horizontal plane. Altitude is just 90 degrees to this. It's a vertical set of axes where we move the telescope up and down.
Did that cause design problems?
Yes, we had quite a few design problems in order to achieve the tracking accuracy required. We've done a lot of studies. In the actual main control loops on the servos, we follow with encoders which are actually incrementing at 0.03 arc seconds. 0.03 arc seconds, that's equivalent to something like the size of a penny on the moon. You know, it's that sort of degree of accuracy. We can actually follow an object, maintain tracking on it over, say, a 1 minute image period to about 0.1 of an arc second, and for an 8-minute period about 0.2 of an arc second.
What remains to be done now before the system's fully operational?
Essentially, we're in the final stages now of tuning the electromechanical drive systems on the telescope. The aim is to achieve maximum accuracy of tracking and to minimize any errors, obviously, to improve the system performance.
The project manager of the William Herschel Telescope is Mike Morris. Mike, what are the main design problems of a telescope of this size and with this kind of mounting?
The problems really are manifold. I mean, we have to design the telescope so that we can construct it on top of the mountain, which is 2,300 meters high. We have to carry all the equipment, concrete and the telescope structure, up a very rough mountain road. Also, of course, as a matter of economy, we've designed this telescope to be an alt-az telescope, which means it's in a sense very much like a theodolite. It has an azimuth rotation and altitude bearing. And this means that you can actually build a telescope much more compact.
Well, the telescope is now very nearly ready. Are there any final problems to be solved?
Of course, there's always a number of problems to be solved in any capital project. We now have to refine a computing system for steering the telescope, and that will go on for some time. I'll be very happy when the instrumentation's ready on the telescope, when we can make full use of it, which should go on next year or so.
Dr. Jasper Wall has come to La Palma to take charge of the observatory here. Jasper, what research are you going to carry out, particularly with this great new telescope, the William Herschel?
Well, for many years, Patrick, the shape of the universe has been my particular concern. And the way I've chased that is to find galaxies, basically through radio searches for active galaxies, and then to use optical telescopes to chase the redshifts of those galaxies and to find out how the numbers of galaxies, active galaxies in particular, pile up in the different redshift shells in our universe so that one can get an idea of how galaxies formed and evolved. Fundamental questions, I'm sure you'll agree. Now, as far as this telescope's concerned, this will enable the chase for the active galaxies to be pursued to ever fainter limits, ever fainter intensities, ever fainter magnitudes, and therefore to greater and greater redshifts. So I think the real excitement, Patrick, is to be able to push that limit of a redshift of 1/2 back to a redshift of 1, which is something like 50% of the way back to the beginning of the universe.
What objects other than active galaxies?
With the William Herschel, I'm certain people will be looking at normal galaxies. They'll be looking at quasars, obviously, which a number of us define, again, a working definition as a type of active galaxy. Or faint objects. I mean, that's what big telescopes are all about, is faint objects, and that's what we'll be chasing with the William Herschel telescope.
The astronomer in charge of the British telescopes on La Palma until earlier this year was Dr. Paul Murdin.
I think one of the most amazing things is that the site itself has kept the promise that it gave to us in 1974 and 5 when the Royal Observatory Edinburgh was site testing it, and the statistics have been fantastic for the clear sky and the seeing, of course. We get average seeing of 1 arc second and even occasional flashes of seeing at a 1/2 arc second, like this picture from the Isaac Newton telescope of the globular cluster M15, when you can quite clearly see in the center the resolved core. This observation was made by Phil Charles at a time when he was studying one of the stars in the cluster, and it was very important for him to isolate that particular star from the rest, something he could only do in good seeing.
Well, what does all this hold out for the William Herschel telescope?
I think it means that the Herschel telescope has to have the potential, and I'm sure the potential is going to be realized, of being the best telescope of the large optical telescopes in the world.
What about the immediate future program?
Future programs for the telescope are organised around cosmology. There's a very interesting program coming up in the next year for the study of IRAS galaxies, galaxies that have been selected by the infrared astronomy satellite. And these are very important from cosmological point of view because the satellite sees galaxies in the northern hemisphere and the southern hemisphere equally and makes a very unbiased sample, so you don't get selection effects like people looking at really nice galaxies and being attracted to them, picking them out. The satellite does it totally objectively.
How did you find La Palma personally, and what now, so far as you're concerned?
Well, I loved it. To this day, it always gives me joy in the morning to see the sun coming up and to see the clouds over the sea below, and to know that I've worked through a night and got a lot of data in my magnetic tapes that I'm going to take away and analyse. I worked at about 120% of my capacity for the last 6 years, and my scientific background suffered. I need to charge my spiritual batteries, and that's what I plan to do. And I plan to strengthen the scientific support, the astronomical support for the Herschel Telescope to make sure it realises its potential in the future.
This is an international observatory, with new telescopes from several nations being built. After all, it's logical to take advantage of the superb conditions up here.
It is a large observatory. There's 10 nations involved in the whole observatory activities. With the UK, there's the Netherlands in partnership with us and ERA. Of course, we're also in partnership with Spain, who's provided the whole site, the road system, the residencia, but is also involved directly in producing instruments now, and of course has telescope time. So it's highly internationalized. But astronomers are very used to working in international organizations. It's a natural thing for us. We always go to someone else's observatory. We observe there with international groups. So there's nothing very hard for us in this respect.
You mentioned telescope time just now. How is that allocated?
Nobody has telescope time of right, but there are a large number of people, astronomers in Britain, in the Netherlands and in Spain, that want to have time. But they have to first think of a very good project. And these projects are all brought together to a time assignment committee, are assessed. There are assessors and there's referees and so on. And the lucky, say, 20% get the time in the end.
What about the links with British universities?
British universities are very heavily involved in the projects we have, both in designing the telescope in the first place and in particular in making the instruments. Most of the instruments we have working on La Palma now, and certainly most for the William Herschel Telescope, will be built in a collaboration between university groups and the RGO.
Looking further afield, what about the links between La Palma and telescopes in other parts of the world?
Most observatories work in some way on common projects. The recent supernova event is a very good example of that. Almost every observatory in the world has had some part to play in that project. But in general, projects which are very lengthy and very labor-intensive in a manner of speaking, that is involving many astronomers in large groups, are usually performed on more than one telescope. So there's a natural collaboration between most observatories.
What do you see as the future developments on La Palma?
10 years ago, the future developments for La Palma are what we have today, particularly the William Herschel Telescope. Planning of that length of time is really needed for these big projects. So what we're doing now is planning for about 10 years' time the next large telescope that we think would be important to have on La Palma for optical astronomy. At the moment, the plan is for an 8-meter telescope. This has 4 times the collecting area that the William Herschel Telescope has, and can attack problems of the kind that really would take much too long on the William Herschel Telescope, even powerful though it is. But such a project would be quite expensive, as you would expect, and we're thinking of international partnerships in projects of that nature nowadays.
Would that be a single mirror telescope or a compound?
It could be a single mirror telescope. In fact, 8 meters is about the size one can make a single mirror, figuring it in the usual way that we are now used to. But it's possible to think of a tessellated mirror, as it's called, with several segments, maybe 30, 40 segments, working with a servo control system that keeps each segment in perfect alignment. Now that is an approach that is used in California. Other places are thinking of single mirrors, and both probably will work.
I've also heard talk of a whole array of 8-metre telescopes. Is that possible, do you think?
Just as radio astronomers have arrays of telescopes to gain both effectively large aperture and a very high spatial resolution, the same thing can be done in the optical region. Now, with an array of, say, 4 telescopes separated by several hundred meters, that will be effectively a very large telescope with the resolution capabilities, in other words, imaging at very high resolution capabilities comparable with very long baseline interferometry in the radio. And that's a very important project to try and proceed with. Each telescope in such an array, of course, can also be worked independently, and it has a dual use, therefore.
So there's a great deal that's laid on store for La Palma, and I imagine that you're pretty optimistic about it.
Very optimistic. Of course, none of these things have been decided. We have, as an astronomy community, to make such decisions yet. But it's clear that such things will be needed. We need to move forward in astronomy, and it's only through getting larger telescopes of this nature and possibly arrays of telescopes that we actually can see how to make the progress we require to do in the future.
Well, exciting times lie ahead, but particularly with this giant new telescope and its great eye. So there it is, the William Herschel mirror, and before long that will be placed inside the telescope itself and used to study objects thousands of millions of light years away. So we're seeing them as they used to be thousands of millions of years ago when the universe was young. And believe me, this mirror is going to tell us a great deal about the universe that we don't know at the present time. It's more than worth all the money and labor spent on it. And if you'd like a copy of the latest newsletter, please send a stamped addressed envelope to newsletter number 26, The Sky at Night, BBC TV, London W12 8QT.